Fourier analysis on the real line. So I will not write for RD and so on. Once we do this, it will be clear. So now we are working with the real line. Okay, did I start recording or not? Yeah. So we are looking at the group R with addition.
Sir,
yeah.
Have you started?
Sorry?
Yeah, okay. Yeah. You have started the recording. I was there.
Okay. Yeah, I did. Yeah, so we are looking at the group. So this is again an abelian group. Okay. It also is a it has a topology, and later we will see the topology and addition go well. In that, addition is a continuous operation in this topology, but we'll come to that when it comes. So what are characters? Characters means we want chi from R to the circle group. These have to be homomorphisms, but also continuous. So this would mean in this case that chi of x plus y is chi x into chi y. Because of continuity, actually, if you do it, if you send 1 to some point, then you can figure out for all rationals. So this is a standard thing. If you know chi of 1 is e to the, let's call it, I don't know whether I should call it 2 pi it or e to the it. What shall I do? Yeah, let me just call it e to the it. There's one. Yeah, actually, it's so what I mean. Did I have a standard notation? I don't know. Should I call it e lambda? What was my definition of e lambda? Was it with 2 pi in the exponent or not? In the beginning, okay, it's not too important, but I have to fix some notation. So what am I doing? E to the 2 pi. So maybe I'll put the 2 pi also. Okay, so let me put. So if you send it to some point, e to the 2 pi it in the.
We want to define it for the identity element. Right?
Yeah. So we want to define it on the real line. So it's a bit like
chi of 0.
So sorry.
Shouldn't it be chi of 0?
No, 0 will go to 1. That won't tell you anything. It's like with integers. 0 will go to 1. There it was cyclic, so you took a generator like 1 and you have to figure out where chi of 1 is. Now real line is not a cyclic group, of course, but but sending 1 or any other point actually. So sending any point, if we figure out, then this implies that by for any integers.
Okay, then we extend to rationals and then to real.
So q times chi of p will be chi of p by q will be chi of p, which will be chi of 1 to the p. So it will be 2 pi tp. So this I should write chi of p by q to the power q will be that. So what it means is that chi of r is e to the 2 pi I t r for all rational r, and then continuity takes care that for any x it is e to the 2 pi I tx. So the characters are then e lambda in the real line, where e lambda of x is e to the 2 pi I lambda x. So I changed the t to lambda. There is no reason, just I mean, yeah, okay. So the characters are exactly this. There are no other characters. So in this sense, the dual as a set R hat is this. R hat is, I mean, okay. Further, the multiplication of characters. That's how we introduce group structure on characters, right? So it's also clear that E lambda into E mu is E lambda plus mu. That's how the complex exponentials work. So in that sense, G hat, so in this case, the dual group R hat is actually R itself. We can identify it with lambda. Instead of writing E lambda, we can write it as lambda. R hat is lambda, even as a, what I mean is, that is, as I said, and R hat with pointwise multiplication of characters. So R hat consists of characters and the group structure there is pointwise multiplication, but that is exactly same as real line with addition. Because of this property that E lambda multiplication E mu is same as lambda plus mu, E is corresponding to lambda plus mu. So like with the circle and so in case of, so this is a bit more nice, simpler in one way, that in case of circle the dual was the Z and Z dual was R. Here R hat is R itself. That is both in some ways simpler and also slightly sometimes confusing. It's better to keep the Fourier domain, and the other side is called time domain. The original thing we can call time domain. So in electrical engineers language, functions on this are thought of as signals in time, where R denotes time. And the Fourier transform is an encoding of the same signal in terms of the frequency contents. Okay, so that will be how Fourier analysis will go. So this is, so it's better to keep the two things separate, although they are both real line. That's where the general locally compact abelian group picture helps. That helps you to keep the concepts clear. Anyway, so this part is clear, right? R hat is the same as R. So once you have that, but again, note, in some ways it is like circle, in some ways it is like this is the, once you understand both the circle and the Z, you are fine. So somewhat similar to, I mean, here and in what follows, in some ways it's similar to the circle group where our characters were complex exponentials, but also similar to Z in other ways. So what is that? For example, these are not in L2. These are not integrable, right? E lambdas are not square integrable. So in that sense, it's more like, so that's why I did both the circle group and the Z. If you know only the circle group, you have to carry the analogy a little bit further. But if you know both the circle group and Z, you will see that this, with the two of them, pretty much all the proofs you can write down for the real line in exactly the same way. So for one, that E lambdas are not L2 functions. So what is Fourier transform? So if I want to define Fourier transform, how is the Fourier transform defined? So it is not defined for L2 functions. I cannot define for L2 functions, but more natural to do it for L1 functions, just like we did in the case of integers. So if f is in L1R, define f hat. Now it's a function where for me always functions are complex valued, as I have been doing throughout the class. Define f hat from R to C by f hat of lambda equal to integral f of x e lambda of x conjugate dx. Formally it looks like inner product, but it's not inner product. This is in L1 and this is in L infinity. That's why we can integrate. It's a bounded function, so you put absolute value, it is integrable. This is well defined. Okay. Also for measures, you can do for mu in M of R. M of R is the space of finite Borel measures on R. For them, you define mu hat of lambda as very similarly E lambda of x conjugate d mu of x over the real line. So in particular, so like in the case of circle, if mu has a density something, let's call it what shall I call it, p of x, let's say. So if mu has density with respect to Lebesgue measure p of x, then mu hat and p hat are the same thing. So Fourier transforms of functions and Fourier transforms of measures are not two arbitrarily defined things. They agree when mu has density p, then mu hat, what we have called mu hat, is the same as what we call p hat here. Okay, in that sense, they are the same. So, but the main point is conceptually you can define it from measures, finite measures and L1 functions, not directly for L2 functions. So what are some of the properties that one can think of here? So before going to L2, we can make some observations here. If maybe I do an example, okay, so just one, so let's take one example maybe. One or two examples. So let's say mu is uniform on -1 to 1. It's an important case. So that is d mu of x is 1 over 2 indicator -1 to 1 of x dx. It has this density. So what is its Fourier transform? Mu hat of lambda is going to be integral over the real line e to the minus 2 pi I lambda x d mu of x, of course, which is actually 1 over 2 -1 to 1 e to the minus 2 pi I lambda x dx, which will give the imaginary part is sine, which is odd, that will cancel. The real part is cosine, so that will give me, well, in any case, it is actually e to the minus 2 pi I lambda x over minus 2 pi I, and then there is an extra factor half, -1 to +1, which is you get that minus that. So what do you get? E to the minus 2 pi I lambda plus e to the 2 pi I lambda. So you get cos, sorry, minus. So we subtract, right? Sorry. So we get here sine of 2 pi I. So sine of 2 pi lambda, because you get e to the 2 pi I lambda minus e to the minus 2 pi I lambda. That will be 2i times sine 2 pi lambda. 2i cancels. 2i cancels this 2i, and I'm left with 2 pi. Okay, actually there was also a lambda here, so 2 pi lambda. So this is the sinc. This is some in. It's called sinc function. Sin x by x, basically, it's a scaling of that. Okay, so that is an example. One more example, which I will not do properly, is the Gaussian measure. Then mu hat of lambda equal to e to the minus lambda square by 2. So okay, so this is I will leave out. Probably many of you have seen a proof of this. You can do it formally very easily. Doing it properly requires a little bit more care. You can use either complex analysis or get a differential equation for mu hat and then prove it. But let me just write it. So Gaussian is more or less its own Fourier transform. So this is a probability measure. So mu hat of 0 is going to be 1. Mu hat of 0 is the total mass of mu. That is going to be 1. That's why there is no 1 by root 2 pi on the Fourier side. Okay. So these are some things. So now let's observe a couple of general properties. Okay, so again, E lambda, there is no question of orthogonality. Okay, uh, so there is not going to be any very good order here. I have not planned properly. You would like to say, okay, sorry, I'm using mu for measures as well as for this. There won't be any ambiguity, hopefully. E lambda, E mu, this makes no sense. But we can only give it indirect meaning. Just like in the case of Z, if you take, let's say, minus L to L, E lambda of X, E mu of X bar, and then integrate with respect to the uniform measure on minus LL, which is 1 over 2L times the Lebesgue measure. Then what you get is, it is very simple. So you will get, it's like here, what do you get? E to the 2 pi I. Yeah, so let me just write it. What will you get here? Can somebody tell quickly? So e to the 2 pi I lambda minus mu into x. So we'll get sine 2 pi lambda minus mu L over 2 pi lambda minus mu L. Is that correct? I mean, something like this. Okay, something like this, but which anyway goes to 0. Actually, this is, by the way, 1. If this is if lambda not equal to mu. And if lambda equal to mu, you will get 1. Sin x by x is 1 at x equal to 0 if lambda equal to mu. And this one goes to 0 as L goes to infinity. So in that sense, the complex exponentials are orthogonal. Okay. They are out of phase. Any two things which are out of phase, they are orthogonal in this weak sense, that in this limiting sense. This itself makes no sense, but this is underlying reason for a lot of things is this. So one should, this is a valuable thing to keep in mind, that it is like this, that they are orthogonal to a large extent. Okay. So if f is in L1 of R, okay, then f hat is a continuous function, bounded continuous function of R. Okay, so in fact, yeah, maybe it is easier to do simpler. If mu is in M of R, then mu hat sup norm is bounded by mu of R. That's direct from definition. Mu hat of lambda, if you put absolute value, you put absolute value here, that is 1. So it gives you the total mass of the thing. And for the same reason, if f is in L1 of R, then f hat has the bound bounded by norm f L1 of R. Okay, maybe I'll start writing just 1 and infinity instead of writing L1, L infinity. The spaces are the same, although one of them is in the dual and the other is on the original. So this is a simple point, but in fact, so it's bounded is okay, but what we are now saying is that it's actually continuous. Okay, so that it is continuous. The reason is also very simple. It's in fact uniformly continuous. But okay, let me just say it is continuous. Why? If lambda n's converge to lambda, then E lambda n of x converges to E lambda of x for all x. So what you have is that f of x E lambda n of x dx. This is what we want to say, f of x E lambda of x dx. Okay, conjugates here. So the fact is, yes, the integrands converge pointwise, and you can use dct because fx E lambda n of x is just bounded by fx, and this is in L1. So dct applies. So this by dct this will converge to that, which is saying a f hat of lambda n, that is f hat of lambda n converges to f hat of lambda. So it's continuous. So L1 functions map to continuous functions. We are not saying anything about the converse way. Just like in the other case, so I didn't explicitly mention here. We studied Fourier transform on the circle, right? So L2 of the circle corresponds to L2 of integers. That is Plancherel theorem. Also measures the Fourier transforms are precisely positive definite functions. That also I stated. Where is that? Yeah. So this is the Herglot's theorem that positive definite functions on Z are precisely Fourier transforms of. So in general, a lot of things in basic Fourier analysis are finding the range of Fourier transform on some subclass of functions. Any such thing is a nice theorem. Okay, if you can find a subclass of functions or measures or any objects, and you can also characterize the range of the Fourier transform on that. In what are all the Fourier transforms of this particular class of functions you have taken? Such theorems are very nice. Many theorems are there of that kind, but L1 itself is, although it's the most natural domain for the Fourier transform, you do not have any other simple characterization of the range of the Fourier transform. Okay, so they are just some functions. You have some necessary conditions, like they have to be continuous, but continuous is not enough. There are other restrictions, and there is no simple characterization of Fourier transform of L1 functions, whether on the circle or on R. Okay, so this is a fact. Anyway, so this is a sufficient condition. Oh, necessary condition, sorry. This is true. It's also true that we have, this is what I had stated earlier, Riemann-Lebesgue lemma. If f is in L1 of R, then f hat of lambda goes to 0 as lambda goes to plus minus infinity. It vanishes at infinity. So overall, if you put the three properties together, Fourier transform of L1 functions are continuous functions which vanish at infinity. So they will also be uniformly continuous for that reason alone. But anyway, so this is a theorem. Proof is almost identical to the earlier case, but this is just once, let me write. Okay. So again, so if f is also smooth, then it is, what you can do is you can look at f of x e to the minus 2 pi I lambda x dx.
So maybe Manju, do you want also compact support?
Not yeah, compact support, is it okay to take compact support, or should I just say vanishing at infinity? Compact support would be better for the reason yeah, so Kaushik pointed out correctly. We'll see in a moment, because we'll do integration by parts. So for the moment, let me take compact support. Okay, fx is cc1 of r intersection L1 of r. This will be f of okay, so let's say it is supported in minus m to m. Anyway, I will just not bother to write that. I will just say that I'll just write minus infinity infinity. So you can write it as fx into e to the minus 2 pi I lambda x over minus 2 pi I lambda. That's the primitive of this one, minus infinity to infinity. And then minus, I'll get here the derivative of f at x, e to the minus 2 pi I lambda x. And then I have a 2 pi I lambda, but that makes this a plus. Now this thing is 0 because f is compactly supported. Meaning you take a large enough interval, but at the two endpoints f value is 0, so this is 0. So what you get is basically 1 over 2 pi I lambda f dash hat of lambda. F dash will be also compactly supported, so it's an L1 function. Okay, so this is okay. So what this shows is, hence f hat of lambda vanishes. Well, f hat lambda is vanishing, like, at least, I mean, it is like big O of 1 over lambda. Okay, as lambda goes to plus minus infinity. And now for general f, in L1 of R, find G in CC of R such that it approximate f in L1 now. Okay, as I said, I will stop writing L1. I will just write 1 and P and so on for locally. I mean, so now everything is on the real line only. Though once sometimes it's on the dual part and sometimes it's on the original part, but we'll make use of the confusion. Anyway, it's R. So I'll just write f minus g L1 less than epsilon and argue. Because if the L1 norms are closed, already we know that the Fourier transforms are closed in L infinity, right? F hat minus g hat will be bounded by epsilon also. Because f minus g L1 norm is bounded by epsilon, f hat minus g hat L infinity norm is bounded by epsilon. And you know that g hat vanishes at infinity. So that shows that f hat and the two lim sup of mod f hat of lambda at both plus infinity and minus infinity are at most epsilon, and epsilon is arbitrary. So this is how you prove Riemann-Lebesgue lemma. Okay, so it's a
CC1 of R, right? G.
yeah, you're right. So I wrote just CC, yeah. So here I wrote CC1. Thanks. So this is CC1 of R. Okay, CC1 of R. So this we have Riemann-Lebesgue lemma. This gives a, so we will see an application, very nice application of this actually. So as a corollary, for example, this is a useful thing. If mu is absolutely continuous, I mean to Lebesgue measure. So this is, that is, it has density. Then mu hat of lambda must vanish as lambda goes to plus minus infinity. Okay, so that is necessary. Yeah, actually I don't know why I made this. So actually, even for this is so I missed one thing. Even for measures, the Fourier transform is continuous. Maybe I just leave it. The continuity part is okay. All right. So that mu hat is bounded. So point property 2, that Fourier transforms of measures and L1 functions are bounded. That is same. Here also the continuity is also the same for both. The Fourier transforms of measures are going to be continuous. Fourier transforms of L1 functions are going to be continuous. But this third property, it's not true. Okay. So this is false. So this is this property is false for measures, general measures. So if so as an example, if mu is delta 0, that is the Dirac measure at 0, then mu hat of lambda is, you have to integrate E lambda against it. It is 1 for all lambda. So mu hat does not vanish at infinity. So atomic measures, you can see, are not going to vanish, but even singular, I mean, so this is, but this is not a converse thing. I mean, we are not saying that if measure is not absolutely continuous, doesn't mean that mu hat cannot vanish. It can. Okay, so it can vanish. So that, but it's a one-way condition. Okay, so that is there. As part of what we have done, we'll extract one more point. Let's extract one more point because it was done here. So if f is or maybe going a little bit more intersection, let's say it's an yeah, so let's say f is in L1 of R intersection C1 of R, and let's say f dash is also in L1 of R. Then this relationship holds. Okay, so then f dash hat of lambda is actually 2 pi I lambda times f hat of lambda. Okay, so this is true. So in other words, this itself vanishes, right? F dash belongs to L1. So this is something I'm saying from here. So in particular, so I'm repeating that. In particular, f hat of lambda will be little o of 1 over mod lambda. Why? Because f dash itself is an L1 function. Its Fourier transform vanishes at infinity. 1 second, just give me a moment. So this is actually f dash, f hat will decay faster. So this is saying that this is again coming back to that theme that I was mentioning. The smoother f is, faster f hat decays. Yes, and the converse is also true. Yes, smoother the f is, both ways it is true. So in particular, so you can do it in the same way. If f is in Ck of R and fk is in L1, then fk hat of lambda will be, just by applying this, you will get 2 pi I lambda to the power k f hat of lambda, which implies that f hat of lambda is actually big O, small o of lambda to the power mod lambda to the power minus k, right? Because this has to vanish. So it's the smoother f is, the faster this is. Okay. And the converse type is also true. If f hat decays, so let's come to that sort of thing. So I'm just going on writing a lot of conclusions. They are all similar to things we have seen. But if there are any questions at any time, please stop me. Okay. I'm not being very organized about it. It's the same properties we have seen. I'm not putting, but I will, okay, wrap it up maybe in the end. And but so now let's go to something else, which is
What is the little o of 1 by lambda as opposed to big O?
big O means it's bounded. So when I write a sequence or a function, so when I write fx equals big O of gx as x goes to infinity, let's say, means fx by gx is bounded. Okay. Lim sup x going to infinity is finite. Whereas little o means that is 0.
Okay, thanks.
Fx by gx actually goes to 0. All these are positive functions. That's how I'm thinking. Mod f of x. Yeah, that's what I want to say. Mod f. So this is going to 0. So that's what it is. So in the original, here I had only said it is big O of 1 by lambda because I was still proving something. But after having proved that, we see it's actually little o because f dash itself is integrable and therefore its Fourier transform decays to 0. We don't know how fast. If you simply know L1 functions, we can say it vanishes at infinity. We can't say how fast. There is no limit to how slowly it can decay. But if it is smoother and smoother, it has to decay faster and faster. Okay. So the converse type is also true. If f decays fast, then okay, smoother f is faster f hat decays. Let's do it the other way. Suppose f decays fast, then the smoother f hat is. So how shall we say that? If f is or which one shall I say? Or shall I say it f hat is decays, then smoother. Okay, let me put it in that way. Suppose mu is a measure and mu hat is in L1. Okay, so this is an extra assumption. So decaying fast. We are assuming mu hat decays fast enough that it is integrable. Then mu has a density which is in fact mu hat at minus x divided by 2 pi. Okay. Okay, that we will see in the proof that the density will be, you can get the density from the Fourier transform by taking another Fourier transform at minus x and divide by 2 pi. Often the check is used, check symbol is used to, instead of writing, it's written as mu hat check of x, but okay, it's so this is going in the other direction. You are assuming decay of the Fourier transform and saying something about the smoothness on this side. I will state more general things like that, but let's so should I yeah, so should I do this, or I mean, can I do it, or should I? Yeah, so the way to do it, how do we do it? Yeah, before this, right, you have to find this. Okay, I didn't introduce the fair kernel in the continuous setting, so let us. Nevertheless, let me mention what goes. I mean, actually, there's no point repeating too much of it. So what we can show is, in fact, so if you look at so in fact, the claim is something more than this actually. Maybe this I should have said first. Okay, so yeah, so maybe I'll put that as a separate point because that will follow from here, the next point. The Fourier inversion, which I come to for measures first. Okay, so I jumped into this decay business, but let's do Fourier inversion for measures. If mu is in M of R, then for all interval, take any interval, if you take mu hat of lambda e to the 2 pi I lambda a minus, okay, all these are subject to possible mistakes, something like this. Yeah, what was the formula actually in the case of So it's the analogous formula here. What did we have here? Right, mu hat of k e to the I k beta minus e to the I k alpha over 2 pi I k sum. So this will become an integral, and here we will have this. Okay, so what we will have is 2 pi I k beta. Okay, I think something like this. So yeah, so there is no minus in the exponent. Let me not put a minus in the exponent. There shouldn't be. 2 pi I lambda b 2 pi I lambda a over 2 pi I lambda. But is this integrable? Why is this integrable? So what happened in the previous case? Why was that? That was, sorry, from. Okay. So in general, it's not integrable. So I have to put minus L to L actually. So this is not going to be integrable. So just like in the circle case, we should take the integral from. Then it is okay. Everything is continuous, right? The mu hat is continuous. So we can integrate this from minus L to L, but let's divide by 2L. Now, do I divide by 2L? Slightly getting confused. Yeah, so it is now it is like this 1 minus mod lambda over 2L. So no, it's not like that. It's not like this. We'll multiply by this fair kernel like thing, which is 1 minus mod lambda over 2L, mod lambda over L, and d lambda. And then if you divide that, I think you have to divide this whole thing by 2 pi. This converges as L goes to infinity to the measure of AB plus half of the measure at the end points. Okay. So this is how, so in particular, if mu hat equal to nu hat, then mu equal to nu. That is one corollary. Because the right side is entirely in terms of the Fourier transform. Whatever limit you may have to take doesn't matter. The right side is expressed in terms of the Fourier transform, and left side you get measures of all intervals, kind of all intervals with where the boundary points have no atoms at least. So therefore you can recover the measure from the Fourier transform. That's what it says. So this is a Fourier inversion formula. Okay, so this is very much like the other one. This is like to be thought of like the fair kernel. This with the, okay, not this, but with some, all this included. So another corollary is that, corollary 1, corollary 2 is that if mu hat is in L1, then what we can do is we can just take L going to infinity here. So this thing, we can apply DCT. We can write mu of AB plus half of mu at the end points is equal to 1 over 2 pi times. This integral becomes minus infinity to infinity. Mu hat of lambda. Now what is this? This becomes e to the, this is the same. This is not going to change. E to the 2 pi I lambda b minus e to the 2 pi I lambda a over 2 pi I lambda d lambda. As L goes to infinity, this goes to 0, right? This goes to 0 as L goes to infinity. Question is, can I apply DCT? Yes, I can apply DCT because this quantity is bounded, okay? This quantity is in fact bounded. So the DCT, why we can apply DCT, that is bounded, as just like in the circle case. E to the 2 pi I lambda b minus e to the 2 pi I lambda a is actually bounded by e to the, I mean, it is the derivative. It's by mean value theorem. If it will be the length of the interval times the derivative at a midpoint. Derivative is an exponential, has absolute value 1. So it's bounded by 2 pi I mod lambda into b minus a. Okay. So that's why this thing is bounded by b minus a, 2 pi I lambda b minus a. Or if you divide by 2 pi lambda, this is bounded by b minus a. So we see that, and this mu hat is integrable. That's what we are assuming. So this will work. So this DCT applies, and in fact it shows that mu of AB plus half mu at the endpoints is bounded by what? It is bounded by 1 by 2 pi integral mu hat of lambda. Okay, if I want to write the bound, it will be mu hat of lambda into b minus a, which shows that it has to be absolutely continuous actually. But anyway, okay, but I will leave it. I will leave a few things as exercise here, or as analogous to the previous one. So this one we will not do. Proof similar to the circle case. Okay. By the way, if anyone wants a reference, for me, my favorite reference for Fourier analysis of measures is actually Feller. I mean, Feller Volume 2 has a very good. So let me give a couple of references here. Maybe I write at the top. So there are many books on Fourier analysis. All the books I have already mentioned, like Katz-Nelson, etc., is also standard references. But also for this specific Fourier transforms of measures and all these type of things I'm talking about now, Feller Volume 2 has an excellent chapter on that. It's very nice, very nicely written. So I always use that. So that's similar to the circle case, so you can do it there. I will leave that. And now this one you deduce from 7. So what you have to do is this, but you have to write this itself as an integral and then reduce this. Okay, so this is an exercise. Again, it is similar to the circle case. It's again very similar to the circle case. So let me just go back and show you there what happened. We had this, if mu is extra, mu hat is in L1, then we get it's a bounded density which is given by mu hat hat of minus t. So we started with the inversion formula, analog of which I have written and left as exercise. We start with this inversion formula and then you get this already I got by applying DCT I got. Okay, so here also I left it as check. Check that mu has this density. You just check that its integral will give you this. Okay, so I got this also, that this quantity is bounded by b minus a times L1 norm of mu hat. That is what I got here. And now I see that I had left the last part as exercise even in the circle case. Maybe you can do it. I mean, it's not at all hard. I mean, you are claiming something is the density. You just check that integral of that over a to b will give you whatever you want, mu of ab. Okay, so that's what it is. So anyway, so any questions so far? Okay, if not, so this is actually, so 0.6 is actually going in the direction of decay of, so this is giving that decay of, so this is saying that decay of mu hat smoothness of mu. This is in that theme. It's the first basic theorem that if mu hat is L1, then mu will have a density. Now let's, once you have that, it's enough to consider functions, right? Because the density is L1 functions. So let me come to this theme, that if f hat decays, if f hat of lambda times mod lambda to the power k is L1, that is, it is integrable, then f must be smooth. Okay. So this is the theme, that decay of f hat implies smoothness of f. Earlier we saw the other way. Smoothness of f implies decay of f hat. Now we are saying decay of f hat implies smoothness of f. Now why such things are true? It's not hard actually. So you just yeah. So why is f smooth? Right. Okay. Okay. So maybe. Yeah, this is where the Fourier inversion will come in. So we said that if f hat is in L1, so maybe I state the first one again. It is actually very similar to the one that I stated for measures. So in fact, the first we prove this f hat in L1 implies f is actually equal to f hat of minus x, almost 12. Okay, so that's what it says. Okay, so f hat will be minus x is fx. Okay, so why is that? It's exactly the same like here. It is but by 2 pi. We have to divide by 2 pi. Okay, so there is a 2 pi factor. This is similar to case for mu hat in L1. See, we assume mu hat in L1 and prove that mu has a density which is given by this. Virtually identical proof will give you that f can be recovered from f hat like this. So let's take this. This is the Fourier inversion formula. Okay, so let's write this. So this is called Fourier inversion formula. Expanding it, we are saying that fx is equal to 1 by 2 pi integral over the real line f hat of lambda, and then I have to take another lambda at minus x. So it will become e to the 2 pi I lambda x d lambda. Oh, just give me a moment. I'll come. Can you hear? Okay. So this is the Fourier inversion formula. So you can, the way you recover f from f hat is virtually the same as you get f hat from f. This is a bit of a coincidence owing to the fact that the dual of R is I itself. Otherwise, you saw in case of circle and Z, one side, I mean, it's always like that. Fourier transform will give back the function more or less with a negation, but one side is a summation, the other side is an integral, and so on. But here it is virtually identical. Okay, so this is the Fourier inversion formula. And now you get from here, actually this is true for all x, by the way, because I wrote here almost surely, but Fourier transform of an L1 function is continuous. So this is true for all x, in fact. This is in fact continuous. Okay, you may in the following sense that originally you may have started with an L1 function f, but if f hat is L1, you can make f a continuous function. That's what is being said, that by you can just make it continuous. And now if f hat is has further this one, so then you can just if f hat has further decay, then f is differentiable. Why? It is did I do it or not? I mean, what did I do here? I assumed f is ck. Okay, I didn't do that. So how do we get this? If f hat lambda times lambda to the k is L1, then f is ck. How do I do that? Right. Okay. So now if okay, sorry. Oh, okay. It's already 1 o'clock. So maybe I will just do a little bit more of this next time, and then I'll just wrap it up next time, whatever abstract theory. So the point is, how do you do this? So you just do, we want to show f is differentiable and all that. You just look at f of x plus h minus. And we will use this to write it.
It's 1 o'clock.
D lambda. Okay. So if we write this, now the point is this is f hat. So by the Fourier inversion formula, we have this. Now we want to let h go to 0. Can we do that? What happens? This one, these things don't depend on h. This will converge to 2 pi I lambda times, I mean, it will just converge to 2 pi I lambda, right? As h goes to 0, this is the derivative of this exponential function at 0. So you'll get 2 pi I lambda. You have to justify dct, use dct. Not only does it converge to 2 pi I lambda, it is also bounded by two pi lambda. For all h, it is bounded by 2 pi lambda. Therefore, and we know that if mod lambda, use dct, assuming mod lambda f hat of lambda is integrable. If lambda times f hat lambda is integrable, then you can apply dct, because this has absolute value 1, to get that f dash is equal to f dash of x is equal to 1 over 2 pi f hat of lambda 2 pi I lambda into e to the 2 pi I lambda x d lambda. Okay, so and so on in that. Okay, I will stop here. I will continue next time. So these are yeah, but let me know also if you want to see more details. I am skipping things because I thought that maybe people don't want to see too many details again and again of the same type. Applications are more interesting, but you're welcome to write to me or tell me in the next class if you would prefer more details. If you want me to go over some of these in at greater length.